Thank you, Ricardo. Hello, everyone. So this is the paper that is accepted in ICIP, which I'm going to present next month as well. So my work is on underwater images. Unlike Dr. Kim's work, mine is more on the visual display aspect. So here we have two underwater images. Underwater images are very typical that they're degraded by color cast and blurring. This is caused by light attenuation, which depends on the water environment and also the scene. By the water environment, I mean the water, different water types. So here you can see one in the typical blue cast and one in the green cast. And by the scene, I mean the distance between the object and the camera, and also the depth of the scene under the water surface. A little bit more about light attenuation. Light attenuation is a combination of scattering and absorption. Scattering increases the light beam's width as the distance increases, therefore you will often see a blurred image. And for absorption, it is the exponential decay in the light intensity. This light attenuation is modulated by the distance and attenuation coefficient that is specific to the water type. The effect is twofold. The first is that along the depth, the illuminant on the scene is actually attenuated. And along the range, the reflected light of the objects, they are attenuated, reduced in intensity. And also there's an increase in the backscattered ambient light. So here we have the degradation model, which is slightly different from that was shown by Dr. Kim, because here what I'm interested in is the scene radiance under a white illuminant. That is J, and I is our degraded image. So if we want to obtain J back from the degraded image, a model-based method will estimate the unknowns in the equation and then invert the equation. While neural networks, if we want to do it end-to-end directly from I to J, we train it on the training data set. But there's one obstacle, as Dr. Kim has mentioned, that is very, very difficult for us to obtain corresponding images of the degraded scene and our target reference image. So the existing trend in neural networks is to either use surrogate reference images that are taken closer to the water surface. However, they're still under a substantial color cost, or to synthesize the degraded image from indoor data sets with known range using the equation that you've seen here. But those indoor data sets, they have very limited color diversities, and in most of the cases, none of these methods actually model the scattering or the attenuated illuminant. The thing with neural network is that your trained network is only as good as your training data. So what we want to do is that, can we synthesize the training data set with all the degradation caused on the scene radiant, while the scene radiant actually contain a diverse color distribution? To do this, we exploit open data that, well, we can use empirical data of the 10 Jerlov water types. So what is left now is that we need to obtain the scene radiance and the range. We use the Syntel dataset, which is a computer graphics dataset that give us a clean path image that reflects the light interaction within the scene, and it also provides us with the relative range between objects. But the clean path image, because it's a CG dataset, that the color does not really reflect that in real life. To do this, we use the luminance channel provided in the dataset that that reflects the light interaction. And because the dataset also gives us the object segmentations, and therefore we recolored each object segment using the color distribution that we previously sampled from the Berkeley segmentation dataset, and we preserve the luminance channel. And here you have an example of our created dataset. So we have the scene radiance. Now what's missing is the scattering function. We implement this range-dependent scattering with successive Gaussian blurring, and we want to make sure that the increase in the spatial width actually follows that of the range. To do that, we decompose the scene into non-overlapping layers with respect to the range in the image, and then we blur each layer successively according to this equation. It might be slightly abstract to think what is happening with this equation, so let's see an example. We start with this clean path image, and starting from the layer that is furthest from the camera, we blur each layer successively. Therefore, if you look at this image, the objects that are furthest from the camera are more blurred than those that are close to the camera. So we have everything we need, and this is an example of our synthesized data set with 10 different Jerlov water types here. I only show the typical examples in the oceanic water, that is the blue cast, and the coastal water that correspond to a green or brown color cast. That was the training data set. And about our neural network, we proposed Cast-GAN, that is a generative adversarial network in which the aim is to have the generator G that mislead the discriminator. We enhance the degraded image I to obtain J star. The architecture of our Cast-GAN is quite simple. For the generator, we use 6 ResNet blocks, and for the discriminator, we use a patch-GAN. So what is slightly more remarkable about Cast-GAN is that the loss function we encourage we encourage 3 things. The first is the misleading of the discriminator, and then we want to encourage the color accuracy between the enhanced image and the reference image, and also the deblurring using a multi-scale SSIM. And the final thing that we did is to avoid very typical artifacts when we are using GAN to generate image by adding in a perceptual loss. So let's see the results of Cast-GAN. This is the degraded image that you've seen before. And this is what Cast-GAN can do to remove the color cast. And then as for the green cast image, you can see that in both cases, Cast-GAN can remove the color cast on objects and enhancing the visibility of the scene. So let's do a bit of comparison with state of the art at the time of submission. So here we have the original image, and on the top row, those are the 2 state of the art neural networks at the time of submission. One of them, the one on the left, UNet, requires images of fixed input size, so it cannot work on images with arbitrary sizes. That would be one problem. And then for the one on the right, UWCNN, that it actually introduced additional cost to the image. The one on the bottom left, that is underwater haze line, is a model-based method and is the only method that aims to remove the color cast from the scene. The problem with this method is that it uses global white balancing, and at the times when the estimation is not correct, that it will introduce a very unnatural red color to the image. And if we see another example, so you observe similar effect in underwater haze line. If we only do a qualitative inspection, it's not really enough. So what we want to do is to validate the color cast removal with a subjective experiment. In this, we asked our participants to compare 2 images and select the one that looks more likely to be under white illuminant, as in the layout that you see here. And we also provide a cannot design option in case the participant find it difficult to tell the difference. In this, we have gathered the responses from 21 participants on 12 original images. And as you can see by the number, that Cast-GAN outperform both the original image, meaning that it can really remove the color cast from the image, and also it outperforms underwater haze line in this case. So just to summarize the work, In Cast-GAN, we have synthesized reference training datasets that include both scattering and the attenuation along the depth and the range, and we have designed loss functions that are specific for the problem. And then we validate the color cast removal with a subjective experiment. All the results, we have put it in an interactive website. So you can actually go to this website and see what Cast-GAN can do. This would wrap up my work. Thank you for listening for this. Back to you, Ricardo.